Hello everyone, we will see how to solve a linear programming problem using graphical method. These kind of problems are quite popular in production, inventory management and scheduling. But as the name suggests, this is linear optimization, so the constraints and objective functions are linear. So the linear function can be represented by a straight line. So in a graph, by representing the constraints through a straight line, you can identify the feasible region, and then you can identify the point which leads to maximum objective function. So let's take one example. In this example, there are two products, product X and Y, and two machines A and B. Each unit of X, product X, requires 50 minutes processing time on machine A and 30 minutes processing time on machine B. So these two machines will be sharing the available machines. So the constraints will be coming on the machine availability. So continue reading. Each unit of Y that is produced requires 24 minutes processing time on machine A and 33 minutes processing time on machine B. So if you note down what is the machine A requirement, then you will see that 50 minutes for X, so it is 50 times X, and then 50 times X and 24 times Y is the requirement for machine A. And probably later on in this question they may be giving what is the available machine times. So with that you can form one of the constraint. So let me continue reading this question. At the start of the current week, there are 30 units of X, so 30 units of X and 90 units of Y in stock. Available processing time on machine A is forecast to be 40 hours. So the machine A's availability is 40 hours. So we have already seen that product X is using 50 minutes of machine A and 24 minutes of product Y. So we can write the constraint as 50 times X plus 24 times Y has to be less than or equal to 40 hours. So constraint A is written here, 50 times X plus 24 times Y has to be less than or equal to 40 hours. So that multiplied by 60, it gives me the minutes, because these numbers are in minutes. So we are just we are representing all the time in minutes. So 40 times 60. So this is the first constraint. So going back to the problem, we can also write another constraint based upon the machine B's availability. Reading the question again, 30 minutes processing time on machine B. So this is nothing but 30 times X plus 33 times Y has to be less than or equal to 35 hours. So that makes the second constraint. 30 times X plus 33 times Y has to be less than or equal to 35 times 60. So that is the second constraint. And so in this statement, they're given the existing stock, that is there are 30 units of X and 90 units of Y are available in stock, and the demand for X in current stock is forecast to be 75 units. So you have to make at least 75 minus 30 units, so that's at least you have to make 45 X units. So that is another constraint. So capturing that as a constraint, X has to be greater than 75 minus 30. So 30 is the available stock and 70 is the requirement at the end of this week. So X has to be greater than 45. That is the third constraint. And Y is forecast to be 95, whereas the available stock is 90 units. So formulating the fourth constraint, Y has to be greater than or equal to 95 minus 90. So Y has to be greater than 5. So that is the fourth constraint. Going back to the problem, So the company policy is to maximize the combined sum of units x and y at the end of the week. So the objective function is x plus y has to be maximum. So since there are pre-existing stock, we have to consider that. Then x minus 45 has to be x minus 45 along with y minus 5. I'm just bringing this 5 to the left hand side, has to be greater. So then that's nothing but x minus 45 plus y minus 5 has to be maximized. So that's nothing but x plus y minus 50 has to be maximized. So this is the objective function, and there are 4 constraints. So the first 2 constraints are coming from the machine time, and third and fourth constraints are coming from the production requirement of product X and product Y. So since we are going to solve this problem graphically, and all these constraints and objective functions are linear equations, they are all straight line equations. So I'm just rearranging the equation so that they are in the standard straight line equation format. So y equal to mx plus c is the standard format. So I'm just trying to rearrange the constraints on that format. So retaining the y term on the left hand side and taking the x term to the right hand side. So it gives me 24y is less than or equal to 2400 minus 50x. Dividing the whole equation by 24, I'm getting y less than or equal to 100 minus 2.08x. And similarly, the second constraint, retaining the y term on the left hand side and taking the x term to the right hand side. So, and then dividing the whole equation by 33, that gives me y less than or equal to 63.64 minus 0.91x. So this is the second constraint, and we have already written the third constraint, that is x has to be greater than or equal to 45, and fourth constraint is y has to be greater than or equal to 5. So now we are ready to draw the graph, and maybe before drawing the graph, it is also better if you compute the x-intercept of these constraints. So the first constraint, that is y has to be less than or equal to 100 minus 2.08. So the y-intercept is 100, and you can find the x-intercept by substituting y equal to 0. So then y equal to 100 minus 2.08x. So x is 48.08. So having known the y and x-intercept, I can mark those points. The 100 is the y-intercept and 48.08 is the x-intercept. So then just connecting these 2 points, I'm getting a straight line. So the constraint is the y has to be less than or equal to the 2400 plus so and so. So the feasible region is the region below this straight line. So I'm just indicating the feasible region by an arrow mark. So the feasible region is this, the region below this straight line. Similarly, for the second constraint, I'm computing the x-intercept by substituting y equal to 0, and then rearranging the x term to the left hand side and dividing them by 0.91. I'm getting the x-intercept as 69.93. So y-intercept is 63 and x-intercept is 69. So this is the y-intercept and this is the x-intercept, 70, almost 70. So I'm connecting a straight line connecting these 2 points. So again, the feasible region is going to be the region below this straight line. So that is marked by this arrow lines. So it's going to be this region. And the third constraint is y has to be greater than or equal to 5. So this is y equal to 5 line. So the feasible region is then the region above this straight line. And similarly, another fourth constraint is that x has to be greater than or equal to 45. So that is on the right hand side of this straight line. So this is the feasible region based upon this constraint. So then if you see considering all the constraints, if you look, we will come to know that only this shaded triangle region is the feasible region. So your optimum is going to lie within this triangle. So obviously this point is having the minimum x and minimum y. So this cannot be the optimum point because we need to maximize x plus y minus 50. So to be an optimum, either x has to be higher or y has to be higher, or both x and y has to be higher. So since it is a triangle, either x can be higher or y can be higher. That means this could be an optimum point, or the point on the x-axis can be an optimum point. So we need to check which one is higher value. So that I am doing by finding intersection of equation 1, that is the constraint 1, and x equal to 45 line, that is this line. So I'm just trying to find out what is the y value at this point. So that is y equal to 100 minus 2.08 times 45, where 45 is the x value. So that gives me y equal to 6.4. So at this point, y value is 6.4. And similarly, you can find what is x value at this intersection. So that can be obtained by subbing y equal to 5, because this horizontal line is y equal to 5 line. So substitute this into the constraint equation. So 5 equal to 100 minus 2.08x. So that gives me x equal to 45.7. So the horizontal length of this triangle is just 0.7, whereas the vertical length is about 1.4. So that is nothing but 6.4 minus 5. So definitely this point, the top point, is the highest point, and you can, this is the optimum point, and the maximum objective there is x value, that is 45, and y value, that is 6.4 minus 50. So that gives me an objective of 1.4. So in this way we have solved this linear programming problem using graphical method. So the key is we need to identify the constraints, and we need to identify the objective function and mark the feasible region, and then identify which point is going to be the optimum. So thank you.